about other boundary conditions? So we have worked up to now with Dirichlet boundary conditions. What about spicing things up and changing things around? Let's look at Neumann boundary conditions. So on one side, instead of imposing the value of u, I'm imposing the value dxu at 0. And I want that to be equal to q. All the rest is the same. We still have the heat equation in one dimension. That is, our omega is still the interval from 0 to L. We're imposing at L the Dirichlet boundary condition. So we are just imposing a value. And we have some initial conditions. We want to write u as the sum of a steady state solution u hat and the transient solution v that depends on x and t. And we want u hat to satisfy the non-homogeneous boundary conditions, while v would satisfy the homogeneous boundary conditions. So when you write the problem for u hat, you have u hat satisfying the second order derivative with respect to x of u hat being equal to 0, and the full non-homogeneous boundary conditions. So second derivative of u hat equals to 0 means that u hat is a first order polynomial, and then we need to check that the value at capital L should be u2, and the derivative with respect to x of u hat at 0 needs to be q. So we retrieve the coefficients of this first order polynomial from the boundary conditions. Then, what does the transient solution solve? Well, it solves the PD, so delta t minus alpha squared delta xx of v needs to be equal to 0. Linearity is important in this case. Then the boundary conditions. Delta xv computed at x equal to 0 needs to be equal to 0. Note this is a different form, but it's the same form as the global PD. Then we impose that v at capital L is equal to 0, and we impose an initial condition that is v at times 0 is equal to f minus u hat. The boundary condition the new boundary condition that we introduced in the PD comes also to the transient solution. And for the transient solution, we can again use separation of variables, retrieving the same form as we did before. And the only difference is now that in the Sturm-Liouville problem, instead of having x at 0 being equal to 0, we have x prime at 0 equal to 0. Notice that it's still a Sturm-Liouville problem on the same interval 0 to L. Has the same format as before, the only difference being what boundary condition we have imposed at 0. So we can solve this. We want x being a sum of cosines and sines. Then what we need to impose is that x prime at 0 be equal to 0. This means that you have a k sin kx computed at 0, that just disappears. So the only term that is non-zero is bk. Cos kx computed at 0. Cos gives you 1, so we have bk equals to 0. You have two options. Either k is equal to 0 or b is equal to 0. Imposing x at capital L equal to 0 gives you a condition on a, k, and b that is on the form of a cos kl plus b sin kl equals to 0. Let's look at the first case first. So would k equal to 0 give you a non-trivial function as a solution? Well, k equal to 0 means that the combination of everything would always be a cos 0 plus b sin 0. And if we place it at x equal to 0, then, and we want that, if we place it at x capital L equals to 0, the function is independent on x, we have capital A equal to 0. But we still have the b being different than 0, but the eigenfunction would still be b times sine of kx, and k is equal to 0. B might be non-zero, but still will give you 0 everywhere. So k is not an eigenvalue because the associated solution of it is trivial. So it's not an eigenfunction. Let's look at the second case. We choose b equal to 0. So the second part is always equal to 0, and we're left with a cos kl. And we need cos k capital L equal to 0. And we can't solve this. We get a solution that is kl equals n times pi plus pi half. You can formulate it in different ways. You can say that is, if you're careful, you can change which values of n you're choosing. But if we go for n pi plus pi over 2, then we have n starting counting at 0, 1, 2, and so forth. And we're checking all the zeros of the cosine. So we have a formula to set k that depends on n for n equals 0, 1, and so forth. Now we have a kn and a phi n that is a cos k and x. As before, the eigenvalue is actually kn squared. Then if you were to choose negative values of n, they would still be associated with the same eigenpair. Then we can solve the solution for t. So we can solve t prime n equals minus alpha squared kn squared capital T. We know the solution is the exponential of minus alpha squared kn squared t. So our full solution is the product of phi n, well, our component solution is the product of phi n times tn. So it's cosine kn x times the exponential of minus alpha squared kn squared t. For values of kn that go from n pi over l plus pi over 2l for n going from 0 to infinity, all the integers. So as before, Vn are solutions of a homogeneous linear problem. Then, Vn being a linear combination of Vn for some chosen coefficients is a solution of the linear problem as well. And we can choose the Cn's such that V satisfies the initial condition. So we have that Vx x at times 0 is equal to this infinite sum of Cn times cos knx. Cos knx comes from the Sturm-Liouville problem, so they are orthogonal. We haven't normalized it, so we have to be careful with that, but they are orthogonal functions. So if you want to set this infinite sum equal to f of x minus u hat of x, well, you can do that by the Sturm-Liouville theory, by imposing Cn being the inner product between f minus u hat and cos knx divided the inner product between cos knx and itself, with the inner product being defined from the Sturm-Liouville problem again as inner product of f and g being equal to the integral from 0 to L of f and g, f times g. Reminder, when can we do this trick of summing things up? Well, if A and B are two solutions of either an ODE or a PDE, then C1A plus C2B is a solution of the differential equation problem if the differential equation is, the full differential equation problem is linear. That means that the differential equation itself is linear and the boundary conditions are all homogeneous. Otherwise, somewhere, something is not adding up anymore.